So Hai, please take away.
Okay, cool. Thank you so much for the introduction, and thank you so much for having me here today. So yeah, I would like to talk about some nonlinear effects in the high eccentricity tidal migration of hot Jupiters. So let me get started by giving you some brief background introduction. So basically, people's interest in exoplanets is largely triggered by the discovery of 51 Peg-b, which is the first exoplanet discovered around a main sequence host. So 51 Peg-b itself is pretty similar to our own Jupiter in the solar system. But what's really surprising here is its orbit. It has an orbital period of only 4 days. So in terms of distance, 51 Peg-b, the distance of 51 Peg-b to its host star is 10 times smaller than the distance from Mercury to the Sun. And in fact, systems like, hot Jupiter systems like this 51 Peg-b, they're not extremely rare. So we have observed something like nearly 300 of them. And people estimate that around every 100 sun-like stars, there will be one hosting a hot Jupiter like 51 Peg-b. The natural question we would like to ask is the following. So how does such a planet form in such a compact orbit? So can they form, for example, in situ? So in other words, so can they form directly at their current day orbit with an orbital period of only a few days? So this is not impossible, but it can also be very challenging. One reason is that it's kind of hard for a gas cloud to collapse directly through gravitational instability. And this is because both the temperature is high and also the Keplerian period is short. So both facts keeps the tumor Q factor large. And as a result, a gas cloud is likely to be gravitationally stable. And then it's also challenging to grow a core sufficiently massive at this location to allow further gas accretion. So in the end, it seems that the in situ formation is unlikely to be the dominant channel to form hot Jupiters. And then instead, the more promising channels are disk migration and high eccentricity tidal migration. So in this disk migration scenario, we have some hot Jupiter form at a proto-hot Jupiter form at a few AU away from its host star, and it resides in a gaseous disk. Then the disk may exert some torque on the planet and helps the orbit to shrink from a few AU to a few hundreds of an AU. I would simply say here that this disk migration channel is a significant channel, and it may be necessary to explain at least a fraction of hot Jupiter populations. But on the other hand, it may not be able to explain all the hot Jupiters. And this is because it's really hard for us to excite some eccentricity through this channel. But we do observe some moderately but significantly eccentric hot Jupiters. Then that means at least a fraction of hot Jupiters should be formed through this high eccentricity tidal migration channel. So in this way, it's very easy to form those eccentric hot Jupiters and warm Jupiters. Those are basically systems in the process of this tidal migration. And also, this is a natural way to produce a large obliquity of the host stars. So that said, for this talk, I would like to focus on this high eccentricity tidal migration channel. Let me give you some big picture of how this high eccentricity migration channel works. So we have, in this scenario, we have a proto-hot Jupiter form a few AU away its host star. And then it becomes a hot Jupiter in essentially a two-step process. So in step number one, the proto-hot Jupiter first gets dynamically excited to a highly eccentric orbit. And this can happen in a few different flavors. For example, it can be through the Lidov-Kozai mechanism. And here, the perturber can be either inclined outer planet, or it can be another stellar companion. And in the case where the perturber is nearly coplanar, eccentricity can still be excited through a process known as circular chaos. And alternatively, the Jupiter may go through a series of scattering processes with other planets, and eventually it gets launched to a highly eccentric orbit. And in any case, once the eccentricity excitation is sufficiently high and the pericenter distance is sufficiently small, then tidal interaction can take over. And we now move on to the second step of this process. So in this second step, tidal interaction dissipates some of the orbital energy to allow the orbit to shrink and be circularized along a trajectory corresponding to roughly a constant angular momentum. So this way, a proto-hot Jupiter formed at a few AU can eventually form a hot Jupiter with a nearly circular orbit. So, well, we have this overall big picture. It turns out that many details of this process, especially the details of tidal dissipation in this process, remain unclear to us. And in fact, this leads to a few observational challenges to this high eccentricity migration channel. So the challenge number one here is about the number of super-eccentric proto-hot Jupiters. We observe a few moderately eccentric hot Jupiters, but very few super-eccentric hot Jupiters. So is this really consistent with our theoretical prediction? So Socrates et al., they realized that we can in fact predict the number of super-eccentric proto-hot Jupiters using the moderately eccentric population. And this is because there should be a steady current of migrating Jupiters. Or in other words, hot Jupiters are formed at a constant rate, and we should expect a continuity along this trajectory of fixed orbital angular momentum. And then if we couple this idea with a tidal dissipation model, where we simply account for the equilibrium tide, and we assume the tidal dissipation is a constant. So basically we parameterize that in terms of a tidal lag, and we treat this tidal lag as a constant. Then we should expect to see a population of super-eccentric proto-hot Jupiters. And that is simply because at this super-eccentric stage, the orbital period is so long, and tidal dissipation is only effective for a small portion of the orbit. So in the end, a planet should spend a long time at this stage. And then Dawson et al. Did a careful search in the Kepler sample. So they estimated that there should be about 4 super-eccentric proto-hot Jupiters based on this constant tidal lag model, but they didn't find any in the data. So this paucity of super-eccentric Jupiter seems to be a serious challenge to this high eccentricity migration channel. And then another potential challenge is about the formation rate of hot Jupiters. So the observed occurrence rate of hot Jupiter relative to cold ones, or so basically our Jupiter-like gas giants, is something around 1 to 10. But then the theory about hot Jupiter formation based on this high eccentricity formation channel, they typically predict a ratio of only a few %. So let's take the Kozai mechanism here as an example and see why this is the case. So kind of the issue is twofold here. One reason is that during the Kozai cycle, the inner binaries eccentricity and inclination oscillates. So the planet will only spend a small portion of time at this highly eccentric stage during the Kozai cycle. And only in this highly eccentric stage can tidal dissipation be efficient because the pericenter distance is sufficiently small. So in the end, there's just not enough time for a planet to migrate within the lifetime of the whole star. And then on the other hand, if the eccentricity gets excited to a too high a value, or the pericenter distance becomes too close to the whole star, that's also an issue because in this case, the planet will simply be tidally disrupted by the whole star. So how to overcome these two issues to slightly enhance the formation rate of hot Jupiter, that's another challenge faced by the theory. But really, I want to emphasize that those things appear to be challenges, and that's only because we haven't put in enough physics in modeling the tide. So in the previous studies, we only accounted for the equilibrium tide, and we typically treat the tidal lag simply being a constant. But in reality, this may not be the case because the tidal lag is not a constant in general. It in fact depends very sensitively on the orbital configuration. So if there exists a tidal circularization mechanism that operates very efficiently at this highly eccentric stage, then it can potentially reconcile many of the tensions I mentioned above. For example, this will make this super-eccentric stage a short-lived transient, and then naturally we are not expected to see those hot Jupiters at this highly eccentric stage. And also, it helps the planet to be decoupled with from the perturber. So basically, because it very quickly shrinks the semi-major axis of the orbit. So once the planet is decoupled from the perturber, it prevents the eccentricity from further increasing, and then this saves the planet from being tidally disrupted by the whole star, and it thus enhances the hot Jupiter formation rate. But luckily, we do have such a mechanism, and this mechanism is known as the diffusive tide, or some people also call it as the chaotic tide. So let me give you a brief introduction of how the diffusive tide works under the linear theory. So here we have a planet on a highly eccentric orbit. At each pericenter passage, the F mode inside the planet receives a tidal kick from the whole star, and this kick turns out to be a constant in amplitude. And then away from the pericenter, the F mode basically behaves as a free oscillator. The propagation phase of this F mode is simply the product of the orbital period times the mode frequency. If we take into account tidal back reaction, then the orbital period is slightly perturbed. This means a phase shift at each pericenter passage. So because that's just a perturbed frequency times perturbed period times the frequency. And then depending on the magnitude of this phase shift, we can actually have qualitatively different evolution trajectories for the tide. And this is very well illustrated by this nice work by Wick and Lai. So if the tidal peak is very weak and the resultant phase shift is much less than 1 radian, then the mode energy will simply oscillate around a fixed value. This value is governed by the 1 kick energy. And here by 1 kick energy, I mean the energy so a planetary mode acquires after a single pericenter passage.
So the energy in the mode doesn't dissipate until it comes back. It comes back, the modes oscillate without dissipation. I mean, the dissipation is negligible. Is that true? That's
yes. I'll actually talk about dissipation, but yes, basically within a cycle, we can very safely ignore any dissipation in this process. And then so under this weak kick limit, in the phase space, the complex mode amplitude basically forms a closed trajectory. So if the 1 kick energy is small, the mode energy will stay small throughout the evolution. And this way, the tidal interaction typically won't be very efficient. But if the tidal kick is very strong and the resultant phase shift is greater than 1 radian, then the mode can actually evolve into a diffusive regime. So in the phase space, the complex mode amplitude will basically try to fill out the entire phase space accessible to it. And then in this plot, we show a zoom-in plot of the initial phase of this diffusive growth. So basically, because of the tidal back reaction, the orbital period is no more a constant. And because the mode energy changes from orbit to orbit, the orbital period also changes from orbit to orbit. So this leads to a random phase of the F mode at each pericenter passage. And it then triggers the mode to grow as a diffusive process, or basically as a random walk process. Once diffusion happens, the mode amplitude grows as the square root of the number of passages, and the energy grows linearly. So this way, the mode can very quickly build up to a very large energy, and this can further make the tidal dissipation very efficient. And then the effect of diffusive tide on the orbital evolution is shown in the next slide. So here in the light, we show a few representative trajectories, including this diffusive tide.
Okay, I'm sorry, I spaced out a little bit, but on the previous slide, so basically the orbital energy is channeled into the energy of these increasing sort of kick. Okay,
Yes.
and so, but without dissipation, what should I think about like the structure of the planet? Like so the energy is growing inside, like what does it, qualitatively, what should I think about what it looks like? So it's just like basically waves propagating around, but nothing changes in the structure, or what happens?
So we at the current moment, we don't include the evolution of the planet at the moment, but it's not, we don't completely ignore dissipation. And in fact, the orbit can evolve because of dissipation. So it's just that the dissipation here can't be a linear dissipation. It's really because of this diffusive process, the mode energy can grow to a large value, and then some nonlinear process will happen, and that removes this energy. And actually, I'll get back to this point later in this talk.
Okay.
But if I take all the energy that is dissipated, if I just bring the planet from the eccentric to, how much is that compared?
Yeah.
Is it a lot compared to what you need to change the structure of the
Yeah,
planet?
thank you. Yeah,
that's actually another point I want to mention in the talks, and that's actually in fact a very key uncertainty of the current study, and that's actually another challenge needs to be tackled in the future. But the short answer is that the amount of orbital binding energy, the change in the orbital energy is actually greater than the binding energy of the planet itself. And that's indeed a key challenge, and that's something we need to solve in the future.
Okay.
But this doesn't seem to be a problem for this particular scenario. Isn't this a problem for any dissipation tide? And if you're going to do it with tides,
yes.
So
as long as the energy needs to be dissipated by the planet, then it will be a challenge here, because it's really just like the initial state minus the final state, and the energy difference here is greater than the binding energy of the planet. So regardless of the dissipation mechanism, it will be a challenge.
I think the usual response is that it's radiated away at the surface.
Yeah, that's indeed the case. And then it kind of also depends on at what time scale this radiation happens. And but yes, I simply mentioned that this is indeed a challenge, and that's actually something I'll get back to later in this talk. Okay, so let's leave those uncertainty aside for a moment, but let's just say somehow the energy gets dissipated, and then so through this diffusive process, the key point is that the orbit can shrink very efficiently, and here the point is that over 10 kiloyears, the semi-major axis of the orbit can shrink by nearly a factor of 10. So this leads to a tidal, essentially like a tidal lag time, something like 10 to the 3 seconds, or in terms of tidal quality factor Q, the Q can be as small as only 10. And then with this, we can revisit the expected distribution of migrating planets as shown in the right here. So if we just use this constant tidal dissipation model as Socrates et al. Did, then we would expect to see this large population of super-eccentric Jupiter. But if we break this Q into for example, just a piecewise function to incorporate the effect due to diffusive tide, and then we will see that the expected number basically goes to 0 at the highly eccentric stage. And this can naturally explain the observed paucity of super-eccentric Jupiters.
So what determines the linear and nonlinear, it's a configuration that determines either it's linear mode or nonlinear mode?
That's actually exactly the thing I'm gonna talk about. So yeah, that's kind of like the big picture of the diffusive tide, and really to understand the physics and to get a complete understanding here, we need to take into account nonlinear interaction. So under the linear picture, we only have the orbit tidally drive a planetary F mode, and now we further allow this planetary F mode to nonlinearly drive some daughter F and P modes. And at the same time, those F and P modes will back react on the parent. So, the process we consider here, I should mention that it's a non-resonant nonlinear process. So this thing that always happens. It doesn't require any threshold energy. So there's a distinction between this non-resonant nonlinear interaction and parametric instability. So here we are not considering parametric process. It's a non-resonant nonlinear correction, and this thing does not require any threshold energy. It always happens. And then, so basically the conservative part of this daughter mode back reaction, it corresponds to an energy-dependent modification of the parent mode's oscillation frequency. And then the dissipative part corresponds to an energy-dependent enhancement of the parent mode damping rate. So one immediate consequence of this nonlinear interaction is that it provides a new channel to trigger the diffusive growth. So recall that the key for diffusive tide to happen is that the F mode at each paracenter passage needs to have a random phase. Under the linear theory, this is achieved by tidal back reaction on the orbital period, which perturbs the orbital period. And with nonlinear interactions, it is now the mode frequency being modified, because mode frequency is a function of energy, and because energy is changing from orbit to orbit, we see that the nonlinear interaction can also produce a random phase, and it therefore opens up a new pathway for this diffusive tide to happen. And more importantly, I want to emphasize that the phase shift due to this tidal back reaction and that due to this nonlinear interaction, they both scale linearly with respect to the energy exchange at each paracenter passage. So formally, the two effects are of the same order of significance. They are same order effects. And if we actually plug in typical numbers involved in this problem, it turns out that the phase shift due to this nonlinear process is actually 5 times greater than the phase shift due to tidal back reaction. So in other words, this nonlinear interaction is actually the main reason causing the diffusive tide to happen in the exoplanet migration. And also because of this factor of 5, it opens up a greater parameter space for hot Jupiter formation. And then we can,
Can I ask a question? This is Wenbin. So you're mentioning the fact that the mode frequency depends on the mode energy in the high amplitude limit
Yes.
is due to the interaction with the daughter modes.
That's correct.
I think even without interaction with daughter modes, if you have any large amplitude harmonic oscillator, meaning that it becomes aharmonic, if you if the amplitude is sufficiently large, that the Fourier in the Fourier space, it's not a simple frequency. It's not at a single frequency anymore, right? So for sufficiently large amplitude, there's always frequency dependence, meaning the energy dependence of the frequency, or the frequency is always energy dependent.
That's exactly the same thing we are saying here. So basically, this nonlinear interaction, this leading order nonlinear correction is the way we use to treat this aharmonic oscillating behavior. The physics is exactly the same. That it's just like when they work under this three-mode interaction picture, the aharmonic of this like large energy behavior that's captured by this nonlinear interaction here.
Mm-hmm.
So they're describing exactly the same physical process. Yeah. So there's a question. Should I keep going or answer a question first?
Jeremy has a question.
Yeah, so just for my sake, just to be clear, so you're not appealing to dissipation by this type of three-mode interaction, just by the change in the frequency, the anharmonicity that it produces. Is that right? I mean, it's not directly that these daughter modes are not directly dissipating; they're just changing the frequency of the F mode, essentially.
So for this part, yes, we only require the conservative part. I'll talk about the dissipative part as so I'll mention the energy dissipation later. But yes, energy dissipation is also important here. Okay. And I'll get to that point in maybe like two or three more slides.
So about the random phase at the pericenter, so will the tidal interaction also somehow like, for example, synchronize like the phase of the oscillation and the orbital period, and that in that case, this random phase would not be the case? Is that possible? So
it seems hard to establish like a synchronization condition. So I think typically this kind of growth will still happen, but there's some complication due to rotation. It's a little bit more involved, but if you're interested, we can talk maybe offline. So yeah. So let's just quickly look at this plot here. So the point I want to emphasize is that if we consider only the linear interaction in this case, then the phase difference between two adjacent orbits is too small. It's less than 1 radian. And therefore, the mode energy will simply oscillate at its 1 kick energy. So in this case, the mode energy doesn't grow to a large value, and the tidal dissipation won't be extremely efficient. But for the exactly same system, as soon as we put in this nonlinear interaction, the contribution, so that adds a little bit to the random phase. And now the phase difference is sufficiently large, it's greater than 1 radian. And that triggers the mode energy to enter this diffusive growth space. And very quickly, the mode energy builds up to a large value. And this can eventually lead to an efficient tidal dissipation. And here is kind of just like a more systematic view of this threshold where the diffusive tide can happen. Here, each dot corresponds to a system we simulate in our and here the y-axis is the maximum mode energy achieved after 500 passages. So really the key, so if a mode enters this diffusive growth space, then we should expect its energy grows linearly with respect to the number of passages. So this is indicated by this black trace here. So for dots scattering around this black line, that corresponds to system undergo this diffusive growth. And those are systems that can experience efficient tidal formation, tidal dissipation, and they can potentially lead to hot drifter formation. And here, really, the point I want to emphasize is that by including the nonlinear interaction, we allow more system to enter this to experience the diffusive growth, and it then opens up the parameter space where hot Jupiter can form.
I think that Jeremy has a question.
Yeah.
Sorry, my fault. I forgot to lower my hand. Apologies.
Yeah. Okay. So and then I should mention that so besides triggering the diffusive tide, nonlinear interaction plays an even more important role in maintaining the diffusive evolution over the long-term evolution. And the key is that in order for diffusive tide to be maintained, the phase of the F mode needs to remain random at each pericenter passage. However, as the orbit decays, the orbit also becomes more tightly bound, and it's harder to be perturbed by the tidal back reaction. So in other words, the fractional perturbation on the orbital period is decreasing as the orbit shrinks. But on the other hand, the nonlinear interaction is less affected here. And that's because for the nonlinear interaction, the natural energy scale is the binding energy of the planet itself. It's not the binding energy of the orbit. So therefore, the fractional perturbation on the mode frequency stays approximately the same. And the end result is that by including the nonlinear effect, this orbital circularization through this diffusive process can proceed further. So without nonlinear interaction, we find that the diffusive tide can only drive the orbital circularization to something like 0.5 AU or an eccentricity of around 0.95. And then including the nonlinear effects, the orbital circularization can proceed further to something more like 0.2 AU. And now, finally, let's talk about dissipation. And so, as people mentioned, so under this, once diffusive tide happens, it can allow the mode energy to grow up to a large value. But in order for the orbit to continuously evolve, to continuous decay, we need to somehow remove this energy. And then under the linear theory, the linear damping is way too small to be relevant here. So what previous study assumed is actually ad hoc energy dissipation prescription. So basically, they allow the mode energy to grow and damp under this diffusive process. And then they set a threshold energy, for example, 10% of the binding energy of the planet. So in terms of tidal displacement, this energy corresponds to the tidal displacement being comparable to the planetary radius. So once the mode grows to this threshold energy, they then assume some catastrophic wave breaking event happens. And once this happens, it suddenly removes 99% of the mode energy. So this way they can achieve an ad hoc energy dissipation. What we find instead is that at least for some Jupiter models, we don't have to rely on this ad hoc prescription. It turns out that the nonlinear dissipation from the daughter modes is sufficient to balance out the energy gain at each pericenter passage. So this prevents the parent mode energy from growing to an unphysically large value, a physical value for this wave breaking to happen, at least for the first 10 kiloyear of the evolution. So although this energy dissipation does not qualitatively change the evolution trajectory of the orbit, I would still like to say that it's significant from a theoretical point of view, because we now have a first principle mechanism for the orbital energy to be dissipated. And also, if we want to couple this orbital evolution together with the thermal evolution of the planet itself, then in that case, we want to quantify the significance of tidal heating. And for that, we need to know where the heat is deposited. And to get the answer here, we need to have a first principle mechanism to show us how the energy is dissipated. So those are the main results of our study so far. And I would like to also mention some potential future projects, and more importantly, some open questions. And in fact, people ask some questions I want to mention already. So let's talk about those things. So first, I just want to mention a simple or kind of natural extension to our work. So I mentioned multiple times that by including the diffusive tide, we can enhance the formation rate of hot ruptures. And let's again take the quasi mechanism as the example and see why that's the case. So if the quasi excitation is relatively mild, or the pericentric distance is relatively large, so I want to emphasize that the key here for diffusive tide to enhance the formation rate is that it decouples the planet from the perturber. And then for weak eccentricity excitation, this prevents the eccentricity from decreasing due to the quasi oscillation. So basically, once the planet gets excited to a highly eccentric stage, the eccentricity stays there and it doesn't oscillate back due to the quasi effect. So this allows the planet to spend more time close to the host star, and this slightly enhances the tidal dissipation. So in the end, this gives the planet enough time to migrate within the lifetime of the host star. And then for systems with very strong quasi excitation, this decoupling prevents the eccentricity from further increasing, and then it prevents the pericentric distance from being too small. So this saves the planet from being tidally disrupted. So the two processes are indicated respectively by the upper and lower envelope in this plot I took from Wick et al. And our study shows that compared to the linear case studied by Wick et al., including the nonlinear interactions, we can further expand both the upper and lower envelopes. And so this is why it can lead to more hot rupture formation. And exactly by how much, that's a question we would like to answer through a future population census study.
I think you said, but no, can you repeat why you have this decoupling? Why these ties lead to the decoupling with the perturber?
Yes. So essentially, the lead of quasi, you can think it as a tidal interaction. So here is the inner binary being tidally disrupted by a tertiary perturber. And if we have this diffusive tide, what it does is that it very quickly shrinks the inner binary's semi-major axis. So this significantly reduces the lever arm, the tide the tertiary can act on. So that's why it decouples this external perturbation. So yes, that's an excellent question. And yes, that's the point I should mention. I should be more explicit about. And then that's the key uncertainty about our study, which is about the evolution of the planet itself. So as we talked about, in order to shrink the orbit from 1 AU to 0.1 AU, the amount of orbital energy needs to be dissipated by the planet is several times the binding energy of the planet itself. And if this happens through this diffusive process, so that means this energy needs to be dissipated within a 10 kiloyear time scale, then the luminosity of the planet can be comparable to the luminosity of a 0.5 solar mass star. So such a dramatic tidal heating can really significantly alter the structure of the planet. And that's something we need to work out in detail. And what's more, associated with this energy transfer, there's also angular momentum transfer from the orbit to the planet. And I want to emphasize that the idea of pseudo-synchronization doesn't apply here, because the pseudo-synchronization condition is derived assuming only the equilibrium tide, whereas here the diffusive growth happens to the dynamical component. And because the dynamical tide is orders of magnitude more efficient than the equilibrium tide, it's unclear if the planet can establish this pseudo-synchronization condition, or if the tidal interaction can actually spawn up the planet to a rate nearly critical rotation. And if this happens, then it may mean that in order to get rid of this excess angular momentum, there might need, so the planet, it requires the planet to experience some significant mass overflow. And this could result in the planet losing more than tens of percent of its original mass in order to dump away this angular momentum gain. And then another significant thing I would like to mention is that we don't really understand what happens to the orbital circularization once this diffusive tide terminates. So even under most optimistic assumption, this diffusive tide can only drive the orbital circularization to something like E of 0.8. What happens next is unclear to us. And sometimes people don't realize this as an issue because the tidal quality factor is just left as a free parameter to be fixed empirically. For example, people find that we can successfully migrate a planet within 1 gigayear if we assume somehow the planet's dissipation is 10 times more efficient compared to our own Jupiter. So that corresponds to something like Q of 10 to the 4-ish. But I want to emphasize that this is only an empirical solution. We don't really know how to make the tidal dissipation or how to make the damping on the equilibrium tide so efficient. If we just do some first principle calculation based on our current understanding of turbulence effect, the quality factor we can get on the equilibrium tide is something only 10 to the 13. And that's way too inefficient compared to this 10 to the 4 value needed. And therefore, it's actually quite serious for us so we need to find out a theory that drives the subsequent tidal evolution from this E to the from 0.8 to 0 regime. And only after we have a complete theory, we can then say, okay, we complete the story about this tidal migration. And also the theory here will be important if we want to make solid predictions on the population of warm Jupiters, because those warm Jupiters, they may, at least a fraction of them may be, those proto-hot Jupiters in this process of migrating. So in order to predict their number density, we need to know what's the tidal dissipation efficiency as a function of eccentricity. So with that, I want to conclude here. So we show that by including the diffusive tide, we can potentially reconcile some observational challenges to this high eccentricity migration channel. So specifically, diffusive tide naturally explains the observed paucity of super-eccentric proto-hot Jupiters. And then we discussed the effect of nonlinear mode interaction to the diffusive tide. So here the key result is that the leading order nonlinear interaction can be viewed as an energy-dependent modification of the parent mode's eigenfrequency. So this is basically, that's just saying that the parent mode is not really an ideal harmonic oscillator, it's an aharmonic. So this frequency is actually energy dependent when the energy is large. And also it enhances the damping rate through nonlinear process. So this energy dependent part, this energy dependent frequency shift, it provides the random phase needed to trigger and maintain the diffusive tide in this evolution process. And then the nonlinear damping part provides a first principle way for the energy to be dissipated. And also, so just like through this discussion, we also know that, well, we're making some progress here. There are actually many open questions that are still unclear to us and that remains to be answered by future studies. So that's all I want to say. Thank you so much for your question. Thank you so much for your attention. I'm also happy to take more questions.
Yeah, so I mean, people here know more about this than I do, but I have an impression that there is really no evidence that hot Jupiters are affected by cosi by another companion star, like observational direct evidence. And so I'm wondering why that is the sort of preferred mechanism for exciting the planet to high eccentricity in the first place, as opposed to planet-planet interactions like in Jurich-Intermain, for example. I mean, is there any reason to believe in terms of statistics that Jurich-Intermain mechanism is less important than Kozai excitations?
I think that's a very good question, and I guess for me, I don't have a answer readily available. For us, it's just because Kozai is something we can very easily analytically model, so it's easy to be coupled through this tidal interaction. But maybe if Josh, you have more evidence.
Yeah, I guess what Nadia is referring to is that people have looked for the stellar companions.
Yeah.
And looked for an excess of stellar companions around stars with hot Jupiters, and there's ambiguous evidence at best that they exist.
Whereas for planet-planet scattering, you wouldn't necessarily see the leftover planets, or they may have even fallen into the star. So I guess what I'm trying to understand is, both start with exciting the planet to high eccentricity. Your process kind of speeds it up, right? It's like that's basically the speeds up the passage of the planet through that phase. So it works either way. So what I'm trying to understand is why is, I mean, maybe you've already answered this question. Maybe there is no good reason to prefer Kozai over planet-planet scattering as kind of like the source of the high eccentricity planets. I don't know.
You kind of, at least in this like two-step picture, they are sort of, can be treated as separate. So we just somehow need the planet to reach this high eccentricity, and then once we get to this stage, tide takes over, and then the presence of the perturber doesn't really play a role. It's probably less clear if for planet scattering. So this planet scatter process, if this diffusive tide can enhance the hot Jupiter formation rate, as we argued in the Kozai case. So that part, maybe there's maybe some
differences. Yeah.
It seems like it would be profitable to study the changes in the internal structure of the planet during this process, because there are a couple of clues from the observations that something happens. One is that the hot Jupiters as a whole have a lower median mass than say the Jupiters at 1 AU.
Yeah.
The other one is that if you look within the sample of hot Jupiters, there's a mass period relation. The shortest period hot Jupiters tend to have higher masses, higher surface gravities than the somewhat less short period hot Jupiters. And those two suggest that there's been some molding of the planets during this process, if it happens.
Yeah. So this is something I put into the supplemental material, but yeah, I guess it's true we might be able to experience some correlation, and that's so in the talk I just simply treated the number density as a function of the orbital configuration alone, but really the tidal interaction is a very complicated process. It depends very sensitive on things like planetary parameters here. And so for example, like this plot shows the threshold for diffusion to happen as a function of planetary radius. So because of this thing, it might suggest that there will be some correlation between, for example, like the final orbital separation with respect to, for example, the planetary radius, and because the Jupiter contracts, this radius can also be an approximation for this whole star age, things like that. But then I put it to the supplemental slide because it's actually tricky to formulate those correlation, because after this diffusive tide, it only happens for 10 kiloyears. After that, there's a very long, slow tidal migration over like a gigayear. Well, how does that wash out this initial correlation? That's unclear. And also, I think we just suggest that in order for the planet to successfully migrate, there needs some mass loss. But again, I think the mass loss mechanism is also a little bit unclear. But I agree. Those are all excellent questions, and they all like deserve more detailed theoretical investigation in the future. And that's exactly things we're aiming as next steps.
You mentioned there was a first principle mechanism for damping energy in the daughter modes, which don't I understand was interaction with convection, convective damping?
Yes. It's the turbulent convective damping of those daughter modes, because those daughter modes they are like either high L F modes or P modes, so they experience more turbulent damping compared to the this L equals 2 F mode.
But if you're dumping so much energy into the planet, is it clear that it remains convectively unstable? Would not depend on where you put the energy. If you put it in the surface, maybe it's no longer convective anymore.
Exactly.
But then this mechanism would you still have damping in that case if you turn off if the convection?
Actually, that might work in favor, because the convective damping might be low, but in that case we might have surface G modes, and so the G modes there, especially the spatial overlap is weaker, but the temporal overlap, because this is a dynamical process, the G modes their temporal overlap with this tidal interaction is actually stronger, and those G modes, because they're close to the surface, they could potentially provide some damping. And then maybe they can be a source for dissipation. But yes, that's an excellent question. Yeah, that's excellent, and that's another reason why we need to couple this thing with the structures change. Yes, exactly.
So the planet, you said it can spin up.
Yes.
Because would it enhance the dynamo process, some magnetic field, and that could help dissipate the energy?
Yes, I think that's another. So we didn't couple this spin evolution, and that's exactly because how angular momentum. So the angular momentum first gets transferred into the mode, and then how does this mode dump this angular momentum to the background star? That's actually itself like a very complicated process. And for example, it goes through this magnetic effect. If there's differential rotation, then it can enhance the magnetic field and then drive some magnetic process so that the planet can eventually reach like solid body rotation. But those are really interesting questions. It's just they are so complicated, and we haven't have an answer for this. We haven't had.
Oh, it's a question online.
Hi.
Yeah.
Go ahead, Jeremy.
Okay, I wasn't sure how many other people might. Thank you for a very interesting talk. A couple of quick comments. There are many things I could say, but on the damping of F modes, this is interesting. I'm not sure how much it will help, but there is an analogy, a strong analogy between F modes and ocean waves on deep water. It's the same dispersion relation, at least for, spherical harmonic indices, larger harmonic indices, square root of the surface gravity divided by the horizontal wave number, which becomes, L over R for stars. And in that case, I believe the rule of thumb in oceanography is that the waves start to dissipate significantly when the acceleration at the peak of the wave. Anyone who's watched ocean waves know that as they get higher amplitude, they actually get quite, their crests become quite peaky when the acceleration is about 1/10 of gravity. I don't know that that would be very important in the star because there isn't much mass near the surface, whereas for the ocean, of course, the density is uniform. So that's one comment. A second comment is maybe more relevant to observations. At least at the level of the linear tide, there's no doubt that when the planet deposits, the planet's tide deposits energy in the F mode, it also deposits angular momentum. And actually, for each tidal harmonic, the ratio of the two is just determined by the angular velocity of the F mode. That the energy deposited is the angular velocity times the phase, angular phase velocity times the angular momentum deposited. So we're putting a lot of angular momentum in the star. Now, if the energy eventually dissipates, that angular momentum is going to be absorbed into the mean flow of the star. So it'll make the star rotate. Yeah. So there's one particular hot Jupiter system that I'm very fond of, and I don't know as much as I should about others, but WASP 12 is an interesting case because the host star is an F star. So it has a very thin convection zone, so we don't think it slows down by magnetic braking. It has a hot Jupiter on a 1.09 day period, and yet the V sign, which transits, and yet the V sign I for that system is Josh probably has better numbers, but I think it's like 2 or 3 kilometers a second. It's actually anomalously low for an F star, which would be hard to understand if that particular hot Jupiter got into its current orbit by a process like this.
Although it could be that sine I is low.
Yeah.
No, but if the hot Jupiter got onto that orbit, it deposited angular momentum, which lies in the plane of the sky. So it would, right, to circularize at that radius, that angular momentum had to go into the star. And so the star should be spinning around an axis that's in the plane of the sky. I would think, unless it's been reoriented somehow, but so I find that puzzling. I mean, it doesn't mean that all hot Jupiters have to form the same way, of course. It could be disk migration in some cases.
Jeremy, why does the angular momentum go to the star?
Well, the total angular momentum is conserved. So if the planet loses orbital angular momentum, the star gains it, unless there's significant magnetic braking.
There could be mass loss entirely away from the entire system.
Yeah, but if it's spinning at at the critical value, which would be like 100 kilometers a second or more, I don't see how it gets down to 2 kilometers a second. Maybe I'm naive. Even with rifles.
Scott has a
Can I ask
question.
my question then?
Yeah,
Maybe
go
I'll.
ahead.
Yeah. So I wonder how. So in your daughter mode dissipation, in what radius is it? All over the entire planet, or is it at which radius is where the dissipation is the strongest? Is it near the surface, or is it all over the entire planet?
It's actually still near the surface because those are still low order P modes. So their oscillation, so they peak at more closer to the surface. Yes, the energy is close to the surface.
Yeah, if that is the case, I think it's unlikely that the planet would entirely be spin up quickly. It's only the surface layers where it's heated that contains the angular momentum. Maybe that is lost because the heating is so strong there, right? And that is probably responsible for this mass loss. Of course, the mass loss might again be accreted onto the star, as Jeremy was saying. I don't know if it will eventually escape all the way, or I think it's likely it will be accreted by the star.
I think that's possible. Yeah, yes. So kind of like regardless where the angular momentum is deposited, the total angular momentum needs to be done. That's comparable to this angular momentum if you just assume like critical rotation. So that's simply governed by, because the energy transfer is on the order of like bending energy. So the total angular momentum transfer, the overall amount needs to be this large. So that's why the total mass loss needs to be comparable to the original planet mass. So yes. So
yeah, I see.
Maybe I could just comment briefly on Nadia's comment. I mean, one of the reasons that high eccentricity migration is attractive is that it does explain the large obliquities seen in the host stars of many hot Jupiters, and that's a natural consequence of high eccentricity migration. In fact, it was predicted theoretically before the obliquities were observed, and it's quite hard to explain in models like planet-planet scattering and disk migration.
Why is it hard to produce in planet-planet scattering? Because they maintain inclinations during scattering?
Well, obviously, if you have an extremely close encounter, you're not going to maintain the inclinations. But yeah, in general, the inclinations are roughly conserved. And with planet-planet scattering, it's also very hard to get stars down by the factor of 100 in semi-major axis that you need to convert a cold Jupiter to a hot Jupiter.
Is there any relation to the lineage formation? This initial high eccentricity?
So could you?
Oh, I just wonder whether there's anything related to the planet formation to have this very high eccentricity to start with.
The question was whether anything related to planet formation can produce high eccentricities.
Yeah, I think that's just because there's all those dynamical process, including quasi and its schedule. But I think so. Kind of like initially they all form sort of like with kind of nearly circular orbit, and then somehow this gets excited to the height.
Other questions? Yeah. So how will stay today and tomorrow? So I think there's still a lot of slots tomorrow. You can sign up for more discussion with them. So and I think it's very nice talk and discussion. Thank you very much.
Yeah, thank you.